Thank you. Okay, so there's some problems I want to work through to make sure everybody's cool beyond just the mechanics of the equations. You understand how this process works. Okay, so if you look on the book on problem 42, all right? So you got planet X with a year that's 200 Earth days. Planet Y circles Omega at 4 times the distance of planet X. How long is a year on planet Y? Okay? So start with, if nothing else, start with a visual. Okay, here's the planet, boom, this is what we got. Period of X, that's the one that's closer. It has a period of 200 days. You're told that planet Y has an orbital radius is that 4 times that, and you want to know how long it's going to take for planet Y to go around. Now, obviously your answer has to be more than 200 days because of the fact that, oh, it's farther out. So the simplest possible, what would have been the simplest possible ratio between orbital radius and period? That would have been the simplest ratio. Do not make this, what'd you say, Elliot?
The T1 squared over T1.
No, yeah, but what would have been the simplest possible ratio? It would have just been a 1-to-1 ratio. So in other words, if this planet was 4 times further away, the period would have been 400 days. Okay? That would have been the easiest possible ratio. So if this is this radius and that's 4 times greater, the period would be 4 times longer. So the period would have been 800 days. Okay, that would have been the simplest possible ratio that existed. Okay? Straight 1-to-1 ratio, not quite that complex, not quite that simple. So again, this equation you're going to have on the front of the test. Okay? You just have to know how to use it, right? So if you're going to compare the period of these planets, you have to be able to emphatically solve this equation for radius, mass, or period, okay? You have to be able to do that. So I'm going to solve this for period. Oh, okay. So that period is going to be 4 pi squared r cubed over big G mass of planet Alpha. And then I'm going to take the square root of that, okay? So if I said, here's this information. Now here's the problem. And a word of caution about this. You don't know what the radius of planet X is, okay? You don't know the number. Neither did Kepler. Kepler worked in ratios. So to actually calculate the period, even though you know that it's 200 days, if you were to try and find the mass of planet Alpha from this information, you couldn't do it because all you know is that the period is 200 days. You don't know the actual distance from Alpha out to the planet. You just know it has an orbital radius. You don't know the actual distance. So with this information, you could not find the mass of the planet. So the only thing we can do is work in ratios. Okay, cool. So now, this would be the planet for X, okay? So if I knew the actual radius and if I knew the actual mass of the alpha, I could actually determine the orbital period of this, okay? It's not what we're after. But what I want you to see is that, hey, this is one way how we can express this period. Now, we're going to work this as a ratio. So what's the other one? Planet Y. Okay? So I'm going to work this as a ratio to the period of Y, which would be 4 pi squared, and that's the radius of X. This would be the radius of Y cubed over big G mass of alpha. Okay? All I did was just set this up as a ratio. Nothing fancy. But here's the story. So because all of this is underneath the radical, I can separate the 4 pi squared big G mass of alpha. Okay? I can pull that out because we're multiplying underneath the radical. So all I'm going to do is rewrite this as period of X is equal to the square root of 4 pi squared big G mass of alpha times the square root of Rx cubed, okay? All I did was separate that out, okay? Didn't do anything weird, I just separated it out because it's all underneath the radical. And then I'm going to do the same thing down here with period y. Oh, okay. So that's going to be 4 pi squared big G massive alpha times the square root of radius y cubed, okay? So all I did, set it up as a ratio. I pulled out the things that are constant. So is all of this going to be the same, the 4 pi squared big G massive alpha, is all of that going to be the same for both planets? Absolutely, okay? That's going to be the same. So this, it's there, but it just drops out, okay? That's what I've got. So what I'm left with is the period of x over the period of y is going to equal the radius of x cubed over the radius of y cubed and the square root of that. Okay? Cool. Now,
I remember this.
so now let's get, since I hate square roots, let's square both sides. So if I square both sides, what do you get?
R squared.
Tx over ty squared equals
Let's see. R cubed.
rx cubed over ry cubed, otherwise known as Kepler's third law.
Yep.
Okay? Now, this is important. These are ratios. This is a ratio. So, if you're clever, and you all are, what are you going to let the radius of planet X equal? 1. Okay. That's 1 unit of distance. Cool. Great. It's 1. So if this equals 1, what are you going to let the radius of y be?
4.
4. Because it's 4 times greater. Cool.
Oh.
Now, you know what the period of x is. Period of x is what, 200 days? Okay? So what's the only thing you don't know?
Period of y.
Period of y. Okay?
Oh my goodness.
If you get done with the test tomorrow or on Thursday and you haven't done something like this, you have done something horribly wrong. Okay? You have done, Elliot.
For showing work, could we not just start with the...
If you just wanted to start with that, that's cool.
Okay.
If you just wanted to start with Kepler's third law, that works too.
Yeah.
Okay? Good with that. So then it's just a matter of solving for it, and you should get, oddly enough, a number much bigger than 200 days. Okay? Good with that. All right, now, let's talk about 43. So 43, we're going to use the same idea. So the satellite A orbits planet speed 10,000 meters per second. Twice as massive as satellite B and orbits at twice the distance from the center of planet A. What is the speed of satellite B? Assuming both orbits are circular. Now, that was a little bit tricky when they wrote this problem. Does the fact that planet B is twice as massive as satellite A, is that a factor? No. Look at all of this stuff that plays into this. Look at every problem you've done with lunar command modules, satellites, whatever. The one thing that you never saw, I never gave you the mass of the satellite. You know why?
Doesn't matter.
Doesn't matter. Okay? Does not matter. Not there. Okay? You couldn't plug the mass of the satellite into these equations if you tried. Now, so here's the story. So here's some random planet. Here's satellite A, and it has a speed of 10,000 meters per second. Okay? And A orbits at twice the distance from the center of the planet. What's the speed of? Okay, satellite B is twice mass and orbits at twice the distance. So here's B, and we want to find its velocity. Now, this is where Kepler's law will do you no good, okay? because Kepler's law is based upon a ratio of period and radius, okay? This is not Kepler's third law. But we can use the same technique, okay? So, and again, you will have this equation on your test. Velocity of any planet is big G, mass is what's at the center over R, okay? This will be on the front of the test. You just have to know how to use it. Cool. So, again, but we are going to employ Kepler's technique of setting this up as a ratio. Okay, nice. So, this would be the velocity of A is going to equal big G, the mass of the planet, over some R. So then we're going to have the velocity of B, big G, mass of the planet, that's the radius of A, this is going to be the radius of B. Okay? Now, if you're clever, and you can look at this, is big G and the mass of the planet going to be the same for both of these? Yeah, so we can do that same thing. Okay, the velocity of A is going to be the square root of big GM times the square root of 1 over the radius of A. All I did was pull out what was constant. Okay, that's all I did. I just pulled out what was constant. And then I'm going to do the same thing down here. Oh, okay, that's going to be big G, mass of the planet times the square root of 1 over the radius of B. Now again, what do you know about big G times the mass of the planet?
They're constant.
Those are constants. Those are just going to cancel out because they're the same values. So now I've taken something very, very complicated, and now I've made it very simple. So do you know what the velocity of A is? 10,000, right? You're given that number, okay? So here's the story. So if you're clever, what are you going to let the radius of A be?
1.
1. What are you going to let the radius of B be? 2, because it's twice as far. Okay? Now, what I would recommend, since I hate fractions, I would square both sides and I'd get VA squared equals 1 over the radius of A, and then I'd have VB squared equals 1 over the radius of B. Okay? Now, what I would do is that I hate fractions, okay? So I'd manipulate those to get rid of, you don't have to, but you could certainly cross multiply. And since this is just kind of like a big ratio, but the whole key to this is that you know what this number is. You know what this number is, you know what this number is, okay? Solve for velocity of B. So what you should see on that one is that it's obviously, because of the fact that it's further out, so here's A and here's B. So don't be afraid to step back and look at an equation and go, okay, well, if you look at this, big G and mass are the same. Radius B has a bigger velocity. So what do you know about the velocity of B relative to the velocity of A? Yeah, the velocity is going to be slower because of the fact that with B, you're dividing by a bigger number. Okay, so that radius is bigger. So you know your velocity of B has to be less than the 10,000 meters per second that it is for A. So if you do this and you get a number bigger than 10,000, you have done something horribly wrong. Okay? Got that? Okay. Now, let's talk about 48. So 48 is probably the most complicated one.
Are you using that book right there? I forgot mine in my car.
No. I don't even know whose book this is. So, there you go.
Thank you.
You're welcome. Okay. So let's talk about 48. So 48 is horribly complicated, but yet simplifies down nicely. So on 48, here's what you got. HD 10180G orbits the pretty at a distance of 1.4 astronomical. What is the ratio of the star's mass to our sun's mass? So this is important once, especially this process, especially now that we've had the capacity to observe exoplanets outside of our own solar system. So to give you some idea of how astronomy has changed, 100 years ago, we didn't know there were other galaxies. We thought the only galaxy that existed was the Milky Way galaxy. We literally thought we were it. So we thought, number one, we just didn't have the telescopes to observe those other galaxies, okay? We thought it was kind of like that whole idea of like a heliocentric solar system. You know, that we didn't like that idea because that means we're like a planet like everybody else. We prefer the geocentric. So we kind of liked the idea that we were the only galaxy. It's like, this is cool. It's just us, okay? And then once we developed better and better galaxies, then we figured out that, well, not only are we not the only galaxy in the universe, there are billions of other galaxies in the universe. And they're all moving away from each other. And not only are there billions of other galaxies, each galaxy holds billions of stars. And so we went from going, oh, here's our little star and we're the Earth and everything revolves around us, to, my God, we are just one of countless billions of stars and planets that exist. So the tough part of finding exoplanets is this. How do you observe them? So one of the techniques they do is that imagine that I darken this room, and this is kind of on scale. So imagine that I darken the room, and Dylan's in the back holding a small flashlight. Okay, I'm not even talking a spotlight. Okay, I'm talking like a small flashlight. And then every once in a while, Gavin is going to have a garden pea, and he's going to take that garden pea and walk in front of that beam of light. And Gavin and Dylan are in the back of the room, and I'm watching this. So the only way that I can tell that the garden pea, which represents a planet, goes in front of that. And so what I would see is that I wouldn't see the garden pea itself directly. What I would see is a slight decrease in the amount of light that I get from the flashlight. And so that's how we know like planets cross in front of stars, is that we can't observe them directly, but we can look and see, man, that light dimmed. And if we can see that repeating, we know how often that light dims, we can know, oh, this is how long it takes for that particular planet to go around that star. So this is what's happening. And so one of the things that you want to be able to do, and again, I can't emphasize this enough, we can't directly measure the mass of stars, black holes, whatever. What we observe is the stuff that orbits them, and from there we can figure out this ratio. So here's what's happening on 48. So here's some star, okay? And this planet orbits this star with a period of 600 days, okay? At a distance of 1.4 AUs. So in other words, this planet is 1.4 times farther away from the sun. If you compare that to Earth's orbit, we're at 1.0 AUs. So this planet is a little bit further out, okay? That's what you got. So what we want is the ratio of the star's mass to our sun's mass. So again, we're not after a number. We're not trying to find the actual mass of this planet. We're trying to find it as a ratio of that star's mass to our sun's mass. Okay, we're not going to say, oh, we're going to take this star and put it on a scale and go, oh, this is the mass of it. Can't do that. So here's going to be your technique. So if you look at what's happening on 48, and again, I cannot emphasize this enough. You start with that 4 pi squared r cubed equals big G mass of the planet, call it alpha, times t squared. Okay? Start with this idea. And again, we're going to set this up as a ratio. So in this situation, we're going to look at a ratio of masses. So here's what I want you to see. The first time we did this thing, we looked at a ratio of orbital periods. The second time we did this, we looked at a ratio of velocities. Okay? Third time we're going to do this, we're going to look at a ratio of masses. Okay? It's the same idea, same technique. Set it up as a ratio of masses. So in this situation, I'm going to compare the mass of planet Alpha to our sun. Okay? So if you isolate this for the mass of Alpha, you're going to have 4 pi squared r cubed over gt squared is going to equal the mass of Alpha. Okay? So if you knew the actual radius of that planet, and you knew the time that it took to go around, you could actually solve for the mass of the planet. Okay? And this is possible. You could actually do this. So you're told that the period is 600 days. You could take 600 days and convert that into seconds, and you could get a number. Cool. Okay? Then you could do the same thing with the radius. You would take 1.4 AUs, and if you knew the distance from the Earth to the Sun, which you could look up in the back of the book, and you can find that number. Multiply that by 1.4, you would have that radius, but that radius would have to be in meters. Okay? And you could plug those numbers in, and you could actually find a numeric value for the mass of this planet. But that's not what you're asked to find. You're asked to find it as a ratio. Okay? So this is going to be planet whatever, HD whatever. Okay? So that's going to be the period of HD, and that's going to be the radius of HD and the period of HD. Now, we're going to do the same thing. This is going to be the mass of our sun, 4 pi squared. Now, which planet do you want to pick? Earth. Let's pick Earth. That seems reasonable. So this is going to be the radius of Earth cubed over GT period of Earth squared. Okay? Now again, what can we drop out?
4 pi squared over g.
4 pi squared over g, that all goes away. Okay? Don't have to worry about that. Those all go away. So, you're given the radius of HD, which is going to be what? 1.4 AUs. So you have this number. That's 1.4 AUs. You're clever because you picked the Earth. So what's the orbital radius of the Earth? 1 astronomical unit. So you have that number. Okay? You're told that the period of HD, and this is where you need to make a decision. You're told that the period of that is 600 days. So if you're going to leave that at 600 days, then you need to put the period of the Earth as 365 days. Okay? So that's an option. The other option is that you can take the 600 days, divide that by 365, and figure out how many years that is. And then you can let the period of the Earth just be 1 year. Now, if you go with that route, the beauty of this is, if you let the radius of the Earth be 1 astronomical unit, and you let this be 1 year, everything on the bottom just goes away, and the only thing you have to worry about is that number up there. Okay? I don't care how, just figure out how you want to do the math. But what you should see on 48, that ratio would make a very, very bad GPA. Just saying. Now, on 49, you're told that it orbits a small star, you're given the orbital radius, and you're told that the mass is 0.13 that of the sun. How long is a year on this world? So what you need to do on 49, you cannot use Kepler's third law. Mainly because of the fact that you are only given information about one planet. So when you do 49, you don't have a choice. You've got to take that AUs and convert that into an actual distance of meters. Go to the back of the book, you can find what one astronomical unit is in meters, because that's the distance from the sun to the earth. So on 49, you have to do smash mouth physics. There's no cute way to do 49. You got to take the AUs, convert that into meters. Take the that mass is 0.13 that of the sun. Look up the mass of the sun, multiply that by 0.13, and then solve that for period. So on 49, you have to start with this, okay? And there's no simple way to do this. This is just pure smash mouth physics. You need to find the actual radius in meters. You need to find the period in seconds. And from there, you can solve for the mass. Okay? Like I said, there is no cute way to do this. And especially like on a problem like 49, if all you do is go at the back of the book and you just write down an answer, and I don't see the numbers that generate that, seriously, just don't even bother, because I'm not going to give you any credit for going to the back of the book and finding an answer for number 49 and writing it down. Okay? Promise you, not going to give you any points. I want to see how that plays out. Now, let's talk about 57. I promise you there's going to be a problem like 57 on the test. I promise you, okay? If you hand in the test, and it's going to probably be like on page 2. If you have not worked a problem like number 57 on the test, you have done something horribly wrong, okay? So let's make sure everybody's cool on how you work number 57. So, no pun intended, put a big star beside number 57. It's going to be a question like it on the test. So, you need the visual. So, this isn't just a pendulum like this where it goes back and forth, okay? This is not the setup. This is a conical pendulum going around like this, okay? So, this is what it's going to be. It's going to be like, if you've ever played like tetherball, where the ball like swings around on the end of a string, tetherball is a conical pendulum, okay? Just more violent. Okay, so here's what you've got. So if you look at the information that you're given, first off, you're told that that's a 500 gram mass on the end of it. Okay, cool. So since that's 500 grams, a 500 gram mass weighs 4.9 newtons. 500 is 0.5, 0.5 times 9.8, you get 4.9. So that's a 4.9 Newton force. You're told that this is 1 meter long, and it swings out with a radius of 20 centimeters. Divide that by 100, you get 0.20 meters. Okay? So there's a whole bunch of things that you can do with this. The first one is realizing that there are only 2 forces, actual forces, acting on that ball. One is the gravitational force acting down, and the other one is the tension. Okay? As far as like actual forces, not components of forces, actual forces. There are only 2. So as this thing goes around in this circle, okay, there are only 2 forces. Gravity trying to pull it down, and the tension in the string. That's it. Okay? That's it. Nothing else. Only 2. Gravity, tension. That's it. But there are components of the tension that we use to figure out what's actually going on. So I'm going to isolate this tension a little bit bigger, okay? So this is going to be this tension. Now, since this thing weighs 4.9 newtons, that means that there's this vertical side over here is 4.9 newtons, okay? Because that's what has to happen. The vertical component of that tension has to balance out the gravitational pull that's pulling it down, okay? So start with this. This is a 500 gram mass. Find the weight of that object. Then you know what the vertical component is over here. Now, the problem is that we need to do trig, but we don't know angles. But we're clever. I want to find this angle, okay? I want to find the angle with the vertical. So I know the side opposite, and I know the hypotenuse.
Ooh,
Oh.
I got it.
So what are you going to do, Gavin?
I'm gonna do inverse sine of the
Beautiful.
opposite and hypotenuse.
So I'm going to do the inverse sine. So Gavin, get us this number. You were all excited about this.
Oh. .54.
So call it 11.5 degrees. Okay? So that angle in there is 11.5 degrees. Cool. Now, at this point, you need to draw this what makes the most sense to you. So Gavin, for the sake of argument, take 90 minus 11.5.
78.5.
So that means this angle out here is 78.5, okay? Pick the angle that makes the most sense to you. So if you want to draw this vertical component out here as 4.9 newtons, and you want to find like the tension, work off the 78.5. If you like this angle in here at 11.5, and you want to find this component, which is the exact same thing, it's just how you want to think about it. This vertical component here is 4.9. That vertical component there is 4.9. It's just however you want to do your triangle. Okay? Just pick one. Either work off that exterior angle of 78.5 or work off that interior angle of 11.5. I don't care. Find the one that you look at and go, oh yeah, that makes the most sense to me. Personally, I work off the 78.5 because it's easier for me to visualize where that force is, okay? So when I worked this problem, I worked off that exterior angle, okay? Which one you do makes me no difference. Just pick the one that makes the most sense to you. So, what I need to find is a couple of things. So, on this one you want to find what's the tension and the strain. So you're trying to find this side of the triangle, the hypotenuse. Now let's just think this through. If the vertical component out there is 4.9 and trying to find the hypotenuse, what does your hypotenuse, which is the tension, have to be bigger than? 4.9. Otherwise you have violated both Euclidean and non-Euclidean geometry, okay, which is kind of cool, right? No. So you know your answer has to be bigger than 4.9. So what I did, because I worked off that exterior angle, and what I'm trying to find, there's that 78.5, and I'm going to try and find this tension, and I know the side opposite is 4.9, okay? So if that's the case, I know that the sine of 78.5 degrees is going to equal that side opposite, which is 4.9 newtons, over the tension. Okay? So, Gavin, what do you get when you find that tension?
5.
Huh?
5.
5, exactly?
Yeah. Pretty
Okay.
much. It's just 5.00 and some numbers.
So, now that makes sense. Okay? It's a pretty shallow angle, so the hypotenuse isn't going to be that much bigger than 4.9. Okay? Cool. Now I have the tension. Nice. So then it wants to know, what's the ball's speed? Well, to figure that out, this is the next leap of faith that you have to take. You know that the centripetal force equals mv squared over r. You know the mass, you have that number. You have the radius, 0.2 meters. You have that number. But you don't know what the centripetal force is. Okay? Small problem. But if you go back up to this triangle, that horizontal, this one right here, that's what represents the centripetal force. Because that's the force that's acting inward to keep this thing moving in a circle. Because if I go around like this, and I let go of it, it turns into a projectile. So that horizontal component here is what's going to be your centripetal force. Now, at this point, there's a myriad of things that you could do. You could use the Pythagorean theorem and you go, oh, there's the hypotenuse, 5 newtons. I know one side is 4.9. I could go c squared minus a squared equals b squared. If you're into the Pythagorean theorem, use that. If you're into trig functions, you could go, oh, okay, hey, I need to find the side adjacent to that 78.5. So this is all jumbled up. So let me draw this again. So that's 4.9 newtons. That's 78.5 degrees. Now, personally, if it were me, I wouldn't use the tension, because if I screwed up my tension calculation, I'm going to screw up the next part of it. If it were me, I'd work off of that angle and that 4.9 Newton force. Okay, that's what I would do. So if you go through this, you get the centripetal force to be whatever that is, like 1. Okay. So if you do your centripetal force calculation, depending on how you do it, you're going to get a value of 1. So now you know what your centripetal force is. That's 1. You know the mass, you know the radius, solve for velocity. I beg of you on these problems, solve the equation first, okay? Do that. Don't randomly put in numbers and then, oh, Burkamp will know what I'm doing. I won't, okay? Solve that. And then once you get that velocity, which should be around 0.6, okay, in meters per second, I think the book gives you some weird number of like 30 revolutions per minute. How they came up with that, I have absolutely no idea. Speed is never measured in revolutions per minute. So then you want to find the period. Now again, there are certain equations that you need to know that are not on your equation sheet. But you've dealt with them enough, it shouldn't be a problem. Velocity is 2 pi r over t. Oh, now you know your velocity, you know the radius, solve for period. Okay?
Oh, okay.
Now the other thing that you could do, you could use centripetal force equals mass 4 pi squared r over t squared. You know the centripetal force because you just found it. You know the radius, you know the mass, solve for period. You could also do that.
Mr.
Okay. What?
Instead of using t, could we like multiply by like 1 over f and then like flip it back?
You could, but I wouldn't, because it's just going to be an extra step that you don't need. Now, if it said find frequency, absolutely. But since it just wants period, you can do it that way, but you're going to go through a lot of steps that you don't need to go through. Okay, so I promise you, if you hand in the test and you haven't worked a problem like 57, you have done something horribly, horribly wrong. Okay, Caitlin, stop that camera for a second. No, you all been sitting, stand up, take a stretch.